Chillo. How's everybody doing today? I'm gonna jump in and open up a file. What a name for a file. But yeah, Slayer. Yeah. Spook all the ghosts away on that one. What I would like to say is first I'm gonna start out with a whole bunch of high and low voltages. Okay? Not a 2. Okay? Just in case anybody is having trouble with anything. I hope you're not, but in case you are. Now, this is all together. And I want you to remember about your spacing. And the order to read from, as you know, this is the ones place, twos. Can I do this without doing all that? No, I can't because everything's hard in life. 16th place, okay. 32nd place. 64th place. Let's say, what is it? 128th place. Okay. 256th place. Let's just call it that and see what happens. Okay. Now, separate that apart. Okay. And, like I said, it's simple. It's very simple. Just remember, it is simple. And you people who know what I'm talking about know exactly how simple this really is. Okay? No worries, man. No worries. E-I-O-U. I-O-U. Alright? Yeah. I think I'm doing a good job separating these. Okay? I did not do a good job by deleting one. But this is what I want to show everybody to always keep in mind whenever you're running with something like this, okay? Because I think I touched on it pretty good, but I'm not sure. Alright? I know that's not right for sure. Okay? Ignore this. Ignore this jumble of stuff here, okay? Do not ignore the fact that these numbers keep incrementing. These numbers keep doubling. Okay? And that these are only places that hold voltages. Okay? And I want you to see how these numbers increment. Okay? This string here is actually all together, of course. Alright? But I separated them so I could show better how to explain binary. Okay? And the only time that you roll over and start again is when you signify the end of your byte. Okay? And in here it would be the ones place again, and twos place again. Okay? Fours place again. Ace place again. Okay? It's the only time that it would roll over. Okay? So I hope everybody's got that. Now, I'm so going to get off that. You people know what I was talking about. I mean, I'm sorry you had to skip 4 toots, right? But, let's say, quit. Let's say, quit. I want to look at CD into C. And I'm going to show you a program. Okay? Say hex dump C. Hello.c. Okay? I'm going to show you this program here. And what I'd like to try today is, you got bits down. You know how to read binary. I want to talk about what's going on here. Okay? This is all RAM. Okay? This is all in your random access memory. This is all in your RAM. And what happens is when you do anything concerning your computer or whatever like that, of course it's got to go through a few channels and everything else. And RAM is what stores that. Okay, if you can imagine RAM as a if you're eating a bowl of cereal and RAM would be the spoon. Okay, your cereal, which is data, gets on the spoon and the spoon goes in your mouth. And what's in your mouth? Imagine your mouth as being the hard drive. Okay, RAM carries the data away. Okay, RAM loads data too. So, you know, when you eat the cereal, that's one thing. When your spoon comes back empty for another pull, just imagine RAM as a spoon. So, whatever we're looking at, like in this instance here, we're looking at our hello.c, right? Okay, we're looking at this hello.c file, which is a source code file to hello world in C. Okay, and whenever we look at a file, we pull it up and it comes into RAM. Okay, we look at it in RAM. When we write to something, we write through RAM. If we have no RAM, well, we can't write to anything. Okay, there's no memory. Okay, ROM is something different, which means read-only memory. A good example of ROM would be something that you can only read from, or instructions that you can only read from, per se. A BIOS chip. Okay, when you boot up your computer, there's a certain select amount of code it takes to boot up the computer. The BIOS reads from read-only memory and only has those instructions. Okay, it might be a collection of 20 different instructions that it can handle. Okay, and after that gets all booted up, one of these instructions will be like, okay, now run the operating system. Okay, but it's only read-only memory. Read-only memory, you can flash ROM. Okay, you can change that, or there is something also called an EEPROM. Okay, which is an erasable programmable read-only memory. Okay, so you could go ahead and put you can erase the read-only memory, but on most, not most, the only thing you need to worry about is ROM. Okay, you have a select few sets, or select few instructions. Okay, and that's the difference between RAM and ROM. Now, they're both memory, yes. This here is written out to the screen, alright, but it's being cycled. If I have a, let me see, I have a 2 gigahertz, say if I have a 2.2 gigahertz processor, this ROM is being refreshed 2.2 gigahertz a second. So if you have 1 hertz is 1 second. Okay, a gigahertz is like a billion. Okay, 1 gigahertz is a billion. So this is being refreshed in memory right now. This is going at 2 billion times a second. Okay, not the screen per se. Maybe I think that's at 50 something hertz. I don't know, or maybe even higher than that. I'm not too good with that, but the processor itself is refreshing this data through ROM at 2 billion times a second. Is that right? I don't know if that's right, but your processor, say if you have a 2.2 gigahertz processor, that means that it goes 2 billion times in 1 second, which is incredibly fast. Okay, a megahertz processor would be in the millions of times per second. Okay, which is definitely a lot slower. Right, that's why you have, you go and you get a faster processor, you can do more calculations per second than with a slower processor. Okay, same thing with when you had the 60 megabyte or 60 kilobyte per second processors or something. It's only 60,000 calculations per second. Alright, and we've seen how our computer reads, and 60,000 might have been good for back then, but not now with all our stuff that we have going on. Okay, so that's that too. I hope you guys get that. But this is being refreshed through RAM, R-A-M, random access memory. This is being refreshed through RAM right now. Whenever we read something, we read it through RAM. We have to have memory to read it, or we have to have memory to allocate something to read to it. Okay, we have to pretty much carve out a block in the world and stick our stuff into it so we can view it. Okay, or a block in memory. Okay, and that's that. So I'm going to skip the RAM-ROM topic, and I'm going to go back to bytes. This here would be considered a byte of information. Okay, let's go 6F. 6F, this other side over here is an attempt to convert. The C switch uses an attempt to convert this hexadecimal format number into something we can read, or ASCII. Okay, this is ASCII, right? It's something we can read. Okay, so for example, 6F would represent a lowercase o, as this pound sign here is represented by 23. Okay, so 23 in hexadecimal format. Okay, if you remember the chart back in 2.1, 23 is a pound sign. 69 is a lowercase I. Okay, it's not an uppercase I, it's a lowercase I. There are differences with that. Okay, that's that. Right? Now, when you look at this here, this over here, this is going to get different when I go into something else, but you can imagine this as an addressing. Okay, this is addressing. Alright, this is not a part of our real data. This is just showing where our data is located on, in this instance, in memory. Okay, this is showing where it's located in memory. I would say this is a pointer, but I'm not going to say this is a pointer. Okay, this is just signifying the address of where that is located in memory. Okay, so that's the source code of the file. Now let's look at the binary of the file. Just a dot out. Okay, let's not do more. Okay, now if you can notice here too, this is the same file. This is hello.c, but look at all this stuff that's in here. Look at the binary of this file. It's just massive, right? It's just massive. And what it's doing, this goes on for a very long time. Okay, and what it does is, where's our actual string? This is actually what it prints out. Okay. I know. Come on, but we've all done it at one time or another. I mean, you can't just type in hello world, that's no fun. Alright? That's the actual string of the file. That's actually our what we said to print out. With C, it's printf. Bash, it's echo. Alright? But look at this binary. This is all addressing here. Well, looking at the binary too, see how huge it is. See how big everything is inside of here. We took a small program. We took a program that was only a few lines and whatever like that, and all this other stuff got inserted into it. Well, all that other stuff is machine code. Okay, that's how your computer is going to read your stuff. Okay, and when we compiled it, look at the source code file here. Hope you can see this. This is our source code file. How big is it? It's only 61 bytes. Okay, because it's only characters. But and characters don't mean anything to a computer. It only means something when you compile that. Okay, and when we compiled it, this grew up to 7.0 kilobytes, or it grew at least 110 times, 100 times. It grew at least 100 times in size. Okay, with stuff that we don't need to pay attention to. We don't need to look at it or anything else like that. It's just all stuff that makes our computer run this stuff. Okay, that's the compilation process. And that is what it does with size. But that's what it does with C. Okay, it's not what it does with machine code. Machine code or assembler, there is no compilation. Okay, I'll get into that later, but there is no compilation with assembler. Alright, and I'll show you the size of a few files, not on this tutorial, but there is no compilation with assembler, because pretty much right now, whenever whatever you type in there is going directly into RAM to be put on the disk as data. Okay, but that's the size of this file. Simple hello dot hello hello world with expletive instead of world. All right, that's that. Now, like I said before, this is only a location of this string of data in memory. Okay, this first block here is only a location of these bytes containing data. Okay, all right, and it's just loaded into RAM, and that's why it's there. Okay, so that's that. Not going to go too much more into what hexadecimal is as far as converting it and everything else like that, but I just want to show you the different parts of where stuff is located. And I want to show you too how you can see that this here at this location at this particular location here, it only has 3 bytes of data. Okay, only has 3 bytes of data, and it stops right there. Okay, now look at the rollover here. Look at these locations. This is at B70. This is at B80. Now, like I said, remember when you're doing a base 10 number system, B70 after you have B7, after you have 70, okay, when you go to 79, okay, the next thing you would expect to have is 80, right? That is true, but only true with base 10. Okay, it's not true with base 10. Our computer's not using base 10. We use base 10 to count, but our computer is using base 16. Okay, so the next order in procession after 79 is not 80. The next number is then 7A. Okay, and then it goes 7B, 7C, 7D, 7E, 7F. Okay, and then after 7F, that's when it becomes an 80. Alright, why is it 7F? Because we use 16 different symbols in our system. Okay? Alright, you guys know that. Now, that's what I want to show you. Look at the rollover, 30 to 40. You think, well, by first assumption, I know I did, by first assumption you figure it's just going up 10 address spaces. It's not. It's going up 16 address spaces at a time. Okay? These increment by 16 different address spaces at a time. Alright? Now, like here, you see it says B0 and then B3. Okay? That's the end of file. There's no more data to load into RAM because that is the end of the file that we just printed out. So of course it would stop here. Okay? So of course that would be the case. And this takes up B0, B1, B0, okay? Because this is starting here. B0, B1, B2, B3. Nothing. Okay? And it rolls over at hexadecimal. Okay? 16 different symbols. And we can even count these out. Alright? 1, 2, 3, 4. 1, 2, 3, 4. No. 1, 2, 3, 4, 5, 6, 7, 8. Okay? This is 8 bytes. Okay? Another 8 bytes equals 16. And that's the rollover to the new line. Alright? Now, yes, this is... Let me small this up. Go look into something else here. I'm going to show you something that's called a high byte and a low byte. And it's very important that you know what that is. Okay? And we'll say hex dump dash C hello.c. We're going to look at our source code file of our hello program. Alright, so it's not all over the place, because it doesn't need, oh Jesus, it doesn't need to be all over the place for us anymore. Okay. Okay. If I can get this right, man, I'll be alright. So, of course, our source code file is not that big. All right, you remember it was 61 bytes long. Okay, but when we assembled it with the C programming language, which added all kind of stuff in there, and that is not bad at all. All right, 7 kilobytes. Hey, who cares? All right. It doesn't matter. There are huge or more massive programs, but it has to load all those things in the C library, okay, and turn this stuff into machine code so we can read it. Right? I can actually show you what it turned into after this, but I would like to talk about high bytes and low bytes. Now you figure because these are over in this area here that these are called maybe high bytes, right? And these over here on the right hand side would be considered low bytes, right? That's not very much the case. Alright? That is not the case at all. These bytes all together are the well, they're not the same elevation, but there is no dividing line here because you see a space right here. There is no dividing line. This is not what I say when I say high bytes and low bytes. This is not high bytes. This is not all low bytes. Okay. This dividing line is just a split or to help you better read something. Okay. That you know there's an 8-byte cluster over here, and so there's an 8-byte cluster over here. Okay. Now with a byte, you can actually split a byte. Okay. And you're going to need this for later on. You can actually split a byte, and this is considered the low byte, and this is considered the high byte. Okay. With B is considered the low byte, and 3 is considered the high byte. Okay. Same thing with 6E. Okay, 6 is the high byte and E is the low byte. Now, what's the advantages of high bytes and low bytes? Why are there high bytes and why are there low bytes? Well, when you're adding data, let's say this. If you have a string of stuff, okay, binary form, okay, you have a string of stuff, and if we will use, let's say, 1, 2, 3, 4, 5, 6, 7, 8, we're going to use 8-bit bytes. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 3, 4, 5, 6, 7, 8. Okay. What happens is, when your data comes in on an 8-bit byte, okay, or a 32-bit byte, you can actually split that. You notice here that these are all 8-bit bytes. Okay? You can actually split this. 1, 2, 3, 4. I can split this last 8-bit byte into 2 4-bit bytes. Or not 2 4-bit bytes. And yeah, they are 2 4-bit bytes really. But I can split this last byte so I could have half a byte here and half a byte over there according to an 8-bit principle. 8-bit byte principle. Okay, but this lower split, when you cut a byte in half, that is called a nibble. Okay, a lower nibble. Okay, so that's, and the reason why that is important is because your machine reads stuff. Say if we had an 8-bit processor, it would take 8 bits of this here to flop data. Okay, but certain things need to come back at certain times, and I will get into that later. But it is possible for you to split a 8-byte chunk. You can split an 8-byte chunk into a 4-byte nibble. Okay, nibble is only a split of a bigger chunk. Okay, but you cannot split an 8-byte. You cannot split an 8-bit byte into a 5-bit chunk and a 3-bit nibble. That's not, for one, that's not symmetric. And it's not divisible by 8. It's not divisible by 4. Okay? You cannot split it into a 2-byte nibble either. Alright? Not with an 8-bit processor. But you can do it with a 4-bit processor. If you only had 4 bits, if you had a 4-bit type of processor, then you can split the last 2 bits into 2-bit nibbles. Okay, that is possible. That is possible, right? But we don't use 4-bit processors. Only 4-bit processor was a 4004. Well, the first 4-bit processor was a 4004 and was used in a calculator. So if you expect to go on YouTube on a calculator, it's not going to happen. Okay, so that is the byte nibble thing. Now, if I go back here, if I go back here and look at our source code file, right? And like I said before, this here is just a better area for you to get the first 8 bytes out of the way. Alright, it's better for you to look at, that's all it is, right? Because this doesn't mean anything when it breaks down into machine language, right? It's only for you to interpret it, okay? Interpret that, okay? You know what I'm saying? But the C switch is just a helper. Anything we see on here is a helper, because our computer really doesn't have to show us anything, alright? But then again, our computer will not work either, because we won't be able to put anything into it, okay? Because we don't understand what's going on. So like I said, this is just 2 separate areas, but not a division between low order bytes and high order bytes. Each one of these bytes contains a low byte and a high byte, and that is for instruction purposes, and that is for processor purposes, which I'll get into in the next tutorial. Okay, this is your low order byte and a high order byte. Now it takes a low order byte and a high order byte to make a bit of data. Okay, so for instance, if we look at 72 here, which is P or R, 72 is R, okay, that contains a low order byte and a high order byte. Alright, now 2 is not R, 7 is not R, 2 and 7 together are R. Okay, but on a deeper, if you look at it at a microscopic level, the low order byte needs to be there, and so does the high order byte. Okay, now also too, if we look at P is 70. P in hexadecimal, P in ASCII is 70 in hexadecimal. Okay, now this also here is a low order byte and a high order byte. Okay, it takes a low and a high to come up with this. Okay, and OA, which is a, what is OA? OA is a dot maybe. What? And no crap, it's a dot here. All right, but there is a low order byte, which is an A, which turns out to be an A. It is not an A, it's a voltage, and a high order byte, which is a 0, which is a voltage, which is a transformation and some machine code crap. This is what we see it. Okay, that's that. That's low and high order bytes. And in the next one, we'll look at some processor stuff. Okay, so I hope you guys dug this. and I will catch you on the next one. Pseudo kill 2677. Have a great day.